So guys, what I want to do today is just take you through a final paper for chemistry. Okay. So what the topic we've been coming off from is chemical change, having a look at redox reactions with regards to the galvanic cell. I'm going to I'm going to look at the electrolytic cell, which is very similar to the galvanic cell. Very similar. And I'm going to have a look at that through this question and then possibly go over it as well a little bit later. But I want to take you guys through that question quickly. And I also want to run you through a past paper as well. I will do separate recordings in my own time that will go up. I'll make it available for you guys. I'll run through an entire chemistry paper, and I'll also run through an entire physics paper, just one of each, okay? Because the principles don't change no matter which year it is. The principles don't change. And a couple things that you guys need to look out for, and I'll answer each question. And you guys, if you need help with answering question 7 or question 8, you'll just go look at that recording to help you. Okay, just make sure whoever entered now is able to enter. Okay, cool, that's fine. Great. So this is November 2017. This was a good year for the physics department, and I'm just going to take you through this paper quickly. Okay, so question 1, always multiple choice. Okay, and that basically 10 questions that try to ask a question of each topic that you've learned throughout the year. They try. Don't always get it right, but they do try. Okay, so I'm not going to go through multiple choice just yet. Question 2 is your organic chemistry question. Okay, now I just want to mention something about organic chemistry. If you do not study, in other words, you don't study your notes, you don't crack open your textbook, make sure you've covered everything in your study, and you don't learn it like parrot fashion, you're not going to do well in organic chemistry. Alright, I can't work miracles in this section either. Okay, it is basically study work. Okay, because if you don't study, you'll not know that this structural formula represents which series. I'll tell you off the top of my head. That's an ester. Okay, I'm looking at an ester. The only way that I would know that is if I studied and I prepared for it. If I looked for the functional group. Okay, so question 2, always organic chemistry. Okay, question 2 is your organic chemistry question where they'll ask you a lot of naming. So write down the name, write down the homologous series, either draw a structural formula. Like this question, they want you to write down the structural formula or draw it. They'll give you a name, and they'll ask you about isomers. You know, they'll give you a functional isomer, or they'll ask you a positional isomer as well. That's question 2. In this question 3, okay, they've given you a graph, okay, and here they ask you a little bit of theory behind the organic compounds, okay, the different series. So this question, give a reason why alkanes are said to be saturated. You would know that if you studied from your textbook. Okay. Same thing here with vapor pressure. That's a definition. You would need to know that as well. And this is basically question 3, also organic chemistry, dealing with a bit more theory. Here you got your question 4. With question 4 deals mostly with the section organic chemistry, where they want you to write down reactions or explain things such as primary, secondary, and tertiary alcohols. Okay. And when I mentioned reactions, you got your addition, you have your substitution, and you have your elimination. Okay, and here they ask you to write down the type. Okay, you would know that if you studied. Cool. And they usually form around 15, 14, and 13, so they definitely range between I would say 10 and 15 marks per question. And here we have question 5, which leaves now the organic chemistry and moves on to the next section, which is reaction rates. Okay, which would lead into the section of acids and bases and chemical equilibrium. Okay, so I want to start going through question 6 because it has the chemical equilibrium question in it. And the chemical equilibrium question is a question that a lot of students struggle with. And I want to make sure you guys get this part right, of course. Okay, so let's have a look at question 6. We'll do it together. Carbonyl bromide, which is COBr2, decomposes into carbon monoxide and bromine according to the following balanced equation, which is COBr2 gas. Okay, get CO in the gas phase plus Br2 gas phase, and enthalpy is greater than 0. Initially, COBr2 gas is sealed in a 2 decimeter container and heated to 73 degrees Celsius. This reaction is allowed to reach chemical equilibrium. Just hold on, give me a second, guys. So question says, it goes on to say, initially carbonyl bromide is sealed in a 2 decimeter cubed container and heated to 73 degrees Celsius. The reaction is allowed to reach equilibrium at this temperature, and the equilibrium constant for the reaction at this temperature is 0.19. Okay, now they do say define chemical equilibrium. Okay, now that's a definition. We can define that obviously if we just learn it, but I want to focus on this the section on just the chemical equilibrium concentration question. Okay, because that involves us drawing the table, of course. Okay, involves us drawing the table, and I know a lot of students do struggle with that. I've seen it over the years. Took me a while to understand it as well, so I just want to go through that question with everybody quickly. Okay, so I'm just going to set the question up. I'm just going to write down the reaction. So the reaction we got was COBr2. Okay, and he gave us carbon monoxide plus bromine. That was also in the gas phase. And they said enthalpy was, they said it was greater than 0? Yes, it's greater than 0. Okay, looks like an endothermic reaction. Anyway, so they tell us at equilibrium it's found that 1,12 grams, so 1,12 grams of carbon monoxide is present in the container. Calculate the equilibrium constant of COBr2. Keep in mind that this equation is balanced, of course. It is balanced. So we construct our table. Okay. Of course, we have, you know, the mole ratio. I always leave a row on top for mole ratio, which I have is basically 1 is to 1 is to 1, of course. And initially, I'm just gonna, not as bad, sorry. There we go. So I have initial mole first, okay, which we know we can just write as Ni. And then I have the change in the mole. Then I have equilibrium, and then I have the equilibrium concentration. Okay, and there's my table. Okay, so I'll just draw the rest of the rows in. There we go. And that's for this one, so there we go, and that's for this one, there we go, and this is for that one there. Okay, so let me just get my wits about me quickly. I'll just be a second. So the initial mole we still need to calculate, because it says at equilibrium it's found that 1,12 grams of carbon monoxide is present. So if we know the formula for mole, we have N is equal to M over big M. So we know what this value is equal to. So we need to first calculate what is the equilibrium mole of carbon monoxide. Okay? So to maybe also clear up some confusion here, we rather do this. Write the ratio here, which is 1 is to 1 is to 1. Here is bromine, here is CO, and here is COBr2. So equilibrium, we found that here, so we're going to be working with the products first. So we need to calculate the number of moles. So we got 1,112 over the molar mass of carbon monoxide, which we know should just be 16 plus 12. So 16 plus 12 should be 28. Okay, and we're just going to put that in on our calculator. Just get my calculator out quickly. Alright, I have it. So I've got 1,12 divided by 28. It gives me an answer of 0,04. So at equilibrium, my equilibrium mole was 0,04. Okay, and all they want after this, the actual question is asking to give me the equilibrium constant of COBr2. Okay, now because everything is in the same mole ratio, I do know that because these are my products, because it's a decomposition reaction, this is 0, that's 0. Okay, I don't know what this is. I'm trying to still figure that out. Okay, I'm not sure what that is. Okay, I'm still trying to figure that out. So I'm going to see if this is even necessary. Let me just check. I know that's 0,04. I know that's also should be 0,04 as well, and that should also be 0,04 based on the fact that they're in the same mole ratio. Okay, just based on that facts, of course. All right, and if that's the equilibrium mole, then we can definitely calculate the equilibrium mole of this value over here as well as that value, but we still need to calculate what is the initial mole. So just looking at this quickly, because they are in the same mole ratio, I just want to check if this it holds true. Let's see quickly. That's the change there, that's the change there, and they're all in the same mole ratio. And surely at equilibrium they all should have the same amount of moles. So they all should probably have 0,04. Because if they have 0,04 as the equilibrium number of moles, then we'll have 0,04 times that. So let's just check if this is going to work. Let me just check if this is going to work. Okay, this should work. Let me just check, guys. So the volume they said was 2 decimeters cubed. So divided by 2 gives us 0,02, and the same thing for this one as well, which is 0,02. And they want the equilibrium concentration. So we can actually just remove this calculation here at the bottom. Yes, we can. Awesome. And we know that the Kc value is 0,19 is equal to, we have the concentration of CO times the concentration of bromine, all divided by the concentration of COBr2, and that should equal the next step 0,02 times 0,02, all over the unknown, which is the concentration of COBr2, which is carbonyl bromide. I think I'm pronouncing it correctly. Okay, so what do we do next is we obviously, that goes to the other side, this comes down to the bottom, so we have the concentration of COBr2 is equal to the product of 0,02. I'm going to go squared because that's what 0,02 times 0,02 is, all over 0,19, right? And if we do that, dang it, my calculator is not in my room. I use my phone calculator, but let's see if I can carry on with that. So I've got 0,02 times 0,02, alright, and I want to divide that by 0,19. Okay, I'll get an answer of, let me just see, 1, 2, 3, 2,11 times 10 to the power of -3 mole per decimeter cube, and I think that should be the correct answer if we check the memo. Yes, we are. Okay, so that one was not the simplest, of course, because all we were able to do was by mole ratio, we were able to fill out the products, we were able to fill out the change. So the change in moles, so because we calculated at equilibrium, it was 0,04. So because at equilibrium, you know, that minus that must give us the equilibrium mole. So we knew that was 0,004. That also is 0,04 because of the mole ratio, 1:1. Same story here. So by natural, because they're all 1:1:1, all the moles for the change row are the same. And then we worked out the concentration for the products. And that's how we were able to work out the concentration by plugging it straight into the formula over here, the concentration of COBr2. Now that we got the concentration over here, which is 2,11 times 10 to the -3, we can obviously work out the this value as well as that value as well. But usually initial is always given. Question 8. This is a typical galvanic cell that we see here. Okay, I'm just going to get my standard table of reductions open, as I know I'm going to need to use it. And first question, or April 1, learners set up a galvanic cell to measure its EMF under standard conditions. Now, what do we mean when we talk about standard conditions? Okay, there's 3 conditions that are standard for the galvanic cell to be tested and executed correctly. Okay, we won't talk about them yet because I think that's a question later on. But write down the name of component Y. Would anybody like to tell me what component Y is? Just off the top of their heads. Anybody?
Can you repeat it? The voltmeter.
It's your voltmeter, yes. Excellent. Okay, we know the standard galvanic cell, the voltmeter that's connected to your 2 electrodes. And we have a presence of electrolytes in either beaker, and of course the salt bridge. Can anybody tell me what's the function of a salt bridge?
I think to complete the circuit.
Yes, that is the function of a salt bridge, is to complete the circuit. But also it completes the circuit, but why does it complete the circuit? It allows electrons to flow, all right, from one electrode to another. That's why it completes the circuit. Okay. Some exams might be a little, as we say, onnodig, unnecessary, by asking you to further explain for 2 marks the function of a salt bridge and not 1. Because 1 mark is completes the circuit, but 2 marks is it completes the circuit by allowing electrons to flow from anode to cathode or cathode to anode or between the 2 electrodes. Perfect. Thank you for that. And now, 8.1.2. This is 1 marker, so we can answer them verbally. Is aluminium, Al, the anode or the cathode? Now, this is a very interesting question because anode is sometimes not on the left-hand side. The anode refers to the type of electrode that is in this little setup, the cell setup. Okay, that's how we determine the anode and the cathode, not by the fact that we are used to seeing it on the left-hand side. Okay, so we go to our standard table of reductions. Use whichever table you feel comfortable. I've explained both these tables already in previous lessons and how to use them. I'm just going to use the table that allows me to find aluminium the quickest, and that's table 4B. Aluminium, the half reaction is Al3 plus 3 electrons gives me aluminium, and that has a value, a cell potential value of negative 1,66. And if I look at the other element or other electrode that we have there, we have Ag, which is silver. So if I go find silver, silver has a positive electrode potential there of positive 0,80 or 0,8. 0,80. So, to conclude, based on those two values, can anybody tell me if Al is the anode or the cathode? I have my answer. Can anybody tell me if it's anode or cathode? Remember, your values, okay, of the cell potential, okay, or electrode potential, should I say, because the cell would be the final value, the overall value, but your electrode potential of aluminium is negative 1,66. And what reaction takes place at your cathode? And what reaction takes place at your anode? Your anode, we know that oxidation takes place there. We know that reduction takes place at the cathode. Okay, so if oxidation takes place at the anode, that means that must be my reducing agent, and if reduction takes place at the cathode, then that means that must be my oxidizing agent, meaning that, as my answer suggests, let me just get, oh wow, I had it perfectly set up. Your aluminium is your anode, which was my answer, because its value was negative. Okay? Okay, so negative value suggests anode. Okay, just to recap again for everybody. Negative value suggests anode. If you think you're going to forget that, write it down. If you look on your table of standard reduction potentials, doesn't matter which one, if you look at it and you find the negative value, and then you go find the other element or the other electrode, which was in this case silver, and in this case aluminium was negative but silver was positive. Okay, your positive value means cathode, your negative value means anode. Now, also something I did mention in the other lessons, what happens if both answers are negative? What happens if both my electrodes actually have negative electrode potentials? The one that is more negative will be your anode, and the one that's less negative will be your cathode. Okay? If one was negative 5, the other one was negative 4, negative 4 is more positive than negative 5. Negative 5 is more negative. So that means negative 5, that value would be your anode, and negative 4 would be your cathode. Okay? No one should forget that now. April 1.3 wants us to write down the overall net cell reaction that takes place in the cell when it is working. This is a nice question. Okay, let's get it going. So, I have a table with me. And so we mentioned that for the anode, it was aluminium, so anode we have Al 3 plus. Well, that's a shocking A. 3 plus 3 electrons. Okay. that should give us, oh no, sorry, I'm writing the reaction the wrong way. Al, we have Al3 plus 3 electrons. Then we have the cathode, which was Ag, and here, just see. I just want to see if there's another one for Ag. I don't see another one because you know there's like 3 or 4 or 5 different copper ones here. So Ag should be this one. Ag plus an electron gives me Ag. Okay. They want the net reaction. Okay, I'm going to extend the line slightly. Okay, they want the net reaction that occurs. Now, of course, if you want to have a net reaction vibe going on here, we have to obviously balance out the electrons. Here I got 3 on top. Here I got 1. Not going to work, right? So obviously, the bottom one needs to be multiplied by 3. Okay, because if I do that, I'm going to end up with, I'm going to write the top one as well. Al gives me Al3 plus 3 electrons multiplied by 3. That's going to give me 3Ag plus 3 electrons. That should give me 3Ag. Right? Now I can write down the net reaction. Okay, net reaction should be, because these will cancel. Okay, so I should have right, the top first, Al plus 3 Ag plus should give me Al3 plus 3 Ag, and that should be my net reaction. Okay, that one was kind of basic. Okay. Cool. Just don't forget, guys, with this one, you must know which reaction is taking place at which node. So we know this is anode, so we know this is oxidation. We know this is cathode, so we know this is reduction, and you must know how to write down the half reactions correctly. And calculate the initial EMF of the cell. Okay, so we know we calculate the EMF of the cell. You know the formula. It's the cathode minus anode. Okay, which is going to equal 0.80 minus 1.66. Okay, and which ends up being 0.8 plus 1.66. Just give me a minute. Calculator, that's what I'm looking for. 0.80 plus 1.66. It should give you 2.46 volts. 8.2, we have consider the half cells P, Q, and R that's represented in the table. And they say that different combinations of the half cells above are compared to determine the highest EMF under standard conditions. Write down the name of a suitable electrode for half cell Q. So half cell Q, we've got chlorine that's in aqueous solution. Alright, and we need to write down a suitable electrode. So an electrode would be this. Okay, to dip into half cell. Okay, so half cell Q, which is Cl2. So let's have a look. I'm just looking on my periodic table. We got chlorine. Now this is available, this information is available in textbook. I think I've gone through something like this before. But the suitable electrode for in this case would either be carbon electrode or platinum electrode. Okay, I would need to just research the reason quickly if I go back to the section, but I'll probably have that answer for you guys a little bit later. Okay, but I need to go back to the section to get that answer. But I do remember somewhat going through why that would be the case. I do remember some way. Excuse me. I'll just need to go find it again. Okay, but not to waste too much time. I'll carry on in the meantime. Okay. Then 8.2.2 state the standard conditions under which the half cells should operate to ensure fair comparison. Okay, now there are three that I mentioned, and I told you that the question was coming up. One, the temperature must be at 100. Sorry, not the temperature. The pressure at 101.3 pascals, and I'll drop my pen. The temperature must be at 25 degrees Celsius, or otherwise 273 Kelvin. And I'm just looking for the third one here. Actually, there's the third one. Just trying to find out where it is. Where is it? Okay, we can just go look. Obviously, just go look for it. Obviously, it's not gonna be much of a thing to find. Of course. Oh, come on, man! I had it like not so long ago. I found it, and I think I still gave it to you guys. But trust me now, not to like have that information in front of me like when I need it. So okay, the concentration, that's the one I was looking for. The concentration must be at 1 mole per decimeter cubed. Temperature must be at 25 degrees, sorry, not 273 Kelvin, that's 0. 298 Kelvin, and the pressure must be at 101.3 kilopascals. Okay, that is the three conditions. 8.2.3, again a 1 mark question. 1 mark question was write down the name or formula of the strongest reducing agent in the half cells above. So what we do here is, here we go obviously to our table of standard reduction potentials. Okay, and we'll go and we'll find the answer over there. We look at the values, okay, of the three half cells that we have there, which we have zinc, chlorine, and copper 2+. Okay, so I'm gonna use table 4b. So zinc 2+, I have negative 0.76. Then looking at the copper 2+, I have positive 0.34, so that's more of an oxidizing agent, because that looks like that's going to be more reduction. And then we have chlorine. Let's find Cl. Chlorine. We use table 4a for that, because I think that's higher up here. Chlorine. Why can't I find chlorine here quickly? Chlorine. Where is chlorine? Anybody else have a table there that can possibly help me locate? Found it. That has positive 1.36. That was more towards the bottom of table 4b, which is more to the top of table 4a. That's positive 1.36. So that looks like that would also be most likely at a cathode, chlorine, as well as copper 2+. So the stronger reducing agent, obviously we know reducing agent works with oxidation, so that answer would definitely be zinc, because it said name or formula. So the strongest reducing agent out of all three half cells is zinc. Then the last one, 8.2.4. Which combination of half cells will produce the highest EMF? Okay, remember it's always anode minus cathode. it's always cathode minus anode. We'll be looking for the EMF of the cell. So we have to choose either PR, PQ, or QR, but no calculation is required. So we know the values of all the half cells, okay, and we know that the calculation goes cathode minus anode. So if we take, for example, chlorine, which has 1,36, looking at that, and copper 2 plus only has 0,34. If I have 1,36 and I'm minus 0,76, which is going to end up 1,36 plus 0,76, which is going to give me quite a high EMF, as if I had to take any other combination. So just looking at those values, I can see that that's going to actually give me the highest value, the strongest voltage. So therefore my answer is PQ. And if we check the memoir, we'll see that PQ is the correct answer there. That's this cell combination of anode and cathode would give us the highest EMF out of all of those options, all three half cells. And question 8 was about 14 marks. Okay, so no joke. But you can see galvanic cell questions in the exam are quite doable, quite basic. It can be achieved. You can definitely get at least minimum, I would say 10 out of 14. If the question is very bad, minimum. Okay. Then I want to go through question 9. Okay, question 9 is going now onto the electrolytic cell. Now, like I said, there are a lot of similarities. One, this is also a cell in which redox takes place. Redox reactions take place within the cell. Okay, you still have an anode and you still have a cathode. So if you have an anode and a cathode, you know you have oxidation and you know you have reduction. Okay, the electrons still flow from anode to cathode in the external circuit. Alright, and ions migrate and conduct electricity through the electrolyte. So, in example, at the anode you have anions, and at the cathode you'll have cations. Anions would obviously go to the anode, and cations would go to the cathode, which are your positive ions, and your anions are your negative ions. Okay? There are a few differences though with the electrolytic cell. The galvanic cell requires a voltmeter, whereas the electrolytic cell requires a power source, such as a battery. Okay? In the galvanic cell, you have the presence of a salt bridge, but in the electrolytic cell, you don't have the presence of a salt bridge. Okay? In your galvanic cell, your anode is negative and your cathode is positive. Here in the electrolytic cell, swapped around. Your anode is positive, your cathode is negative. Because now we've hooked it up to a battery. A little different. In your redox reactions in your galvanic cell, you'll end up with a positive cell potential value, but in your redox reactions, alright, in a electrolytic cell, which is called non-spontaneous, they will end up being negative. Okay? And of course you don't have two beakers here, you have just one. So that's just face value things of what we can see there. Okay? So, with an electrolytic cell, I'm also just going to teach from this question as well. You're going to use a DC battery, which is direct current. Okay? You will 9 times out of 10 use a DC battery, right, or power source. Unless, of course, they state that they have used a rectified alternating current or alternating current power source. But your power source is DC, direct current. So to answer the first question, what type of power source, AC or DC, is used for the reaction? is DC. Okay, direct current. Okay. When an electric current 9.2 passes through the concentrated Cu copper chloride solution, the mass of electrode P increases. Okay? Now, the similarity here is that when the mass of a certain electrode increases, okay, that obviously means a lot of ions are being attracted to it. Alright? Something happening there. Okay? Is electrode P the cathode or anode? And write down the relevant half reaction to support your answer. Okay? So, to answer that question, okay, electrode P is your cathode. Why? Because that's where reduction takes place. Okay? Because if reduction is gain of electrons, then that means if I'm gaining, then the mass should be also increasing. Alright? So, electrode P should be my cathode because that's where reduction is happening. So that's gain of electrons. Okay? And if I am now separating Cu and Cl2, then that means the substance that is being reduced or that's being collected around the electrode P is copper. So I write down the copper 2 plus half reaction, which is found on my table. As you can see, Cu 2 plus in aqueous solution plus 2E gives me copper. Because if the mass is increasing, that means solid copper is forming around the electrode. Okay, like I said, if you've watched the movie Into the Blue, you would see this type of cell being used. Okay, 9.3, nice question here. The impure copper contains zinc impurities which are oxidized to zinc ions. Refer to the relative strengths of oxidizing agents to explain why zinc ions will not influence the quality of the pure copper produced in the cell. Okay? Well, if we look at our relative strengths in our table and we compare the values, we can see that obviously zinc has a value of negative 0.76, while copper has a positive 3.4 electrode potential. Okay, with that being said, boys and girls, copper is a stronger oxidizing agent as opposed to zinc. Zinc is a weaker oxidizing agent. In fact, zinc is actually a stronger reducing agent. Okay, and copper is being reduced. All right, it's being reduced. Okay, because it has a positive value. So zinc, because zinc is a reducing agent and not an oxidizing agent, the copper actually overpowers it. Okay, because it is a stronger oxidizing agent than zinc. To compare my answer to the memo, okay, copper 2 plus, okay, I just said copper, but copper 2 plus is stronger oxidizing agent than the zinc 2 plus ions. Okay, therefore the zinc 2 plus ions will not be reduced to zinc, which is zinc in the solid phase. In other words, there won't be any zinc forming on the electrode like copper. Question. All right, no question, because it's so small, it's so minute or so minor, because copper 2 plus is a stronger oxidizing agent than the zinc 2 plus ions. Okay, because zinc 2 plus is a reducing agent, that's going to be oxidized as opposed to being reduced. Okay, it's not going to come out of the aqueous solution phase into the solid phase as what's happening here with copper. Copper's coming out of solution into solid phase. It's being reduced. 9.4, electrodes P and Q are now replaced with carbon electrodes, both of them. Okay, They are now replaced at with carbon electrodes. So the same concentrated solutions are still there, are still present. This is 1 mark question. So what will be observed at electrode Q, because now it's carbon, okay, there will be chlorine bubbles, chlorine gas bubbles that will be formed around the electrode Q, because both of them are P and Q. But what's going to happen at Q, because Q is now, well, Q is, if P was the cathode, Q is still your anode. What's going to happen now, if it's the electrode is now carbon, according to science and chemistry, that there will be chlorine bubbles that will take place around the electrode. Okay, and that is actually in the section somewhere and should be available within every textbook as well, as to why that happens. But usually that would usually happen between chlorine and carbon. And the last question, how will concentration of the electrolyte change as the reaction proceeds? Choose from decreases, increases, decreases, or remains the same. Well, the concentration would definitely decrease because you are oxidizing and you are reducing. Okay, you got 2 electrodes, you're trying to separate carbon or copper chloride, so definitely the concentration is definitely going to be reduced. Okay, the solution's definitely going to change color. I'm correct in saying that copper chloride, that does have a certain coloration to it. So if you are reducing, if you are reducing, or not reducing, if you are separating the two, okay, copper goes to the cathode to be reduced and starts collecting on the electrode, and chlorine goes to the other, or goes to the anode and starts bubbling. Obviously, the concentration within the in the solution obviously is going to change. Okay, it's not going to stay the same. I'm not adding any more copper. I'm not adding any more chlorine. I'm separating the two. So therefore, the concentration by default or by intuition must decrease. And that is the electrolytic cell question, which is 9 marks. The electrolytic cell is usually mark allocation is less than your galvanic cell questions. Galvanic cell they ask a little bit more of. But we can see that just by going through this question of the electrolytic cell is not very difficult either to understand and comprehend like the galvanic cell. So I thought I'd just take you through the question to show you guys you got nothing really to panic for if you just know your stuff and just learn your stuff well. This is chemistry, guys. This is not physics. You don't need to really think analytically for it. You just need to think more logically for this paper. But with physics, you need to think a lot more analytically because you need to analyze situations, analyze scenario. Here, you just need to think logically and connect the dots with what you have studied and prepared for the exam. Literally, that's all. And that's about it. I just want to pause the video quickly. So thank you, Matrix, for joining me, just taking you through a past paper lightly, just letting you see the questions and then maybe clearing up some fog about what you should be looking for when answering a question, and especially on the galvanic and electrolytic cells. So we'll see you next week. We will go through some more specific questions.